Hello, this is the CSE 04 project, which is graph-based SLAM for differential drive robots. Alright, here's graph-based SLAM for differential drive robots. Participants were Hansen He, Jaeyoon Kim, and Arush Toshikanda, which is me. However, Hansen and Jaeyoon are not available to record this right now. So, thank you to our mentor, Mr. Carlos Isaac Espinoza Ramirez. Right. Here's table of contents. We'll start to about an introduction to SLAM, motivation for it, types of SLAM, and the benefits of. Next, we'll look at SLAM visualizations. These are visualizations we've coded to show how SLAM works and what it does. Next, we'll go on to robotic setup. We'll talk about ROS, Docker, Gazebo. These are all important hardware and software components we use for our project. And then later, we'll go on mirrors and SLAM and the challenges faced and how we use April tags and to overcome this. All right. First, here's GNSS-based systems. GNSS-based systems or global navigation satellite systems are navigation system which uses constellations of satellites orbiting the Earth to send precise geospatial location and timing information to users back on Earth. This is useful for autonomous navigation as it provides necessary information around the environment for vehicles or for a user to navigate around, which is useful. Next, we'll talk about GNSS is very good in a lot of cases. However, it still comes with challenges. First off, some challenges that GNSS might face is that one, there's such thing as urban canyons where tall buildings, such as which are made with concrete, wood, and metal, these all make it hard for GNSS signals to go through. GNSS signals often get obstructed to something called radio obstruction, and this distorts the GNSS signals. This leads to errors in timing, geospatial information, and more inaccuracies when giving data back to users on Earth. This is very unreliable. Also, there's no GNSS signals indoors as well because of the metal and concrete, as this often gets deflected. This often deflects the GNSS signals. For example, if you're in a mall, right, and trying to go to a coffee shop, however, you use GPS and it says you're at a clothing shop when you're clearly not. This is an example of GNSS distortion in action, which is very unreliable. Also, there's more errors in GNSS in strong weather events, such as solar flames, leading to more inaccuracies in GNSS. This is a very big problem, and how do we solve this? Well, we use something called SLAM. Simultaneous localization mapping, which stands for SLAM, enables the robot to construct a map of an unknown environment while simultaneously determining its own location within the map. SLAM is split into many parts. There's filter-based algorithms, optimization-based SLAM, and some review sensor used. As you can see, we will only be focusing on graph-based SLAM, which is a type of optimization-based SLAM, to find the optimize a path around a room or location. As you can see here on the right image, this is an example of SLAM in action. Higher images shows like how high up image is, and SLAM was used to map this environment, which is one of the many ways it's used. Because SLAM can map an unknown environment when you can't really use GNSS systems, so it's a way to navigate systems without GPS. An unknown system. Next here is GTSAM. This is Georgia Tech Smoothing and Mapping, or GTSAM, is a library that uses factor graphs to represent SLAM problems. And GTSAM applies efficient optimization algorithms to estimate a robot position and landmarks around an unknown environment. As you can see here, this is an example of one of the factor graphs creates. So these dots, like U1, and U to all of which like UN, these are odometry measurements from the sensor. The blue nodes are robot position, so robot pose. The black dots M1, M2, M3, M4, and so on are landmark measurements, and then these are connected by an edge to a landmark position, like L1, L2, and these are connected through landmark measurements. These are the factor graphs that GTSAM uses to optimize a pathway. Next, we'll move on to offline visualizations. So, what an offline visualization is, it's an example of SLAM in action, not using, it's an example of SLAM using data that's like offline. Basically, SLAM gets all the data like around an environment ahead of time. And so you can see here, SLAM uses this data to optimize its path. The red path is just purely reliant on odometry sensors. As you can see, the red path is very unorganized, it's not very optimized, it's very messy, and not very like reliable to navigate around the environment. However, green is what we use after SLAM optimization. It's what we use after we given all the data to the robot. As you can see here, the green is much more clean, organized, and very direct and concise. It's very good. All right, next here's online visualization. So online visualization is basically SLAM, except it uses all the data it has in action. It doesn't get any of its data ahead of time. It uses data real time, which is much harder to code. Um, First, for example, here's four types shown here. There is the odometry, which is odometry is like pure sensors. Because you can see, there's very low correlation. It's not very reliable. You should not use that at all. It's like very bad. Next, it's next we have EKF SLAM, which is a type of SLAM. Uh, EKF SLAM, which is a type of SLAM. And basically, as you can see, it's much more clean. It's much more close to the gray line, which is the true path. The blue line, which is EKF SLAM, is much more closer than the red line. Is much like more accurate than the red line as it's closer. And you see SLAM, and you can see from the graph, EKF SLAM has an average total of around 24-ish error pixels, where odometry has an average of about 40 error pixels. And lastly, we have ISAM 2, which stands for Incremental Smoothing and Mapping SLAM. This is GTSAM's ISAM. It's created by GTSAM. GTSAM is the most accurate, as the smallest amount of pixel errors, which is around 5.17. Very accurate, and it has basically the best, basically. This online visualization of SLAM provides groundwork for future experiments with real sensors, since it's very useful. It can also help us integrate. We can also integrate this with ROS2 and Docker in the future. All right. Now here is some of the software components we use. It's ROS and Docker. ROS, which stands for Robot Operating System 2. We used ROS to Humble, which is a more updated recent version of ROS. Is a modular open source framework largely reliant on nodes, topic services to build robotic application. It's very useful for simulating complex robot behavior, as all the nodes, topics, and service tools work together to build a complex robot and allow us to do many specific tasks. Next, you'll see use Docker. Docker allows us to run ROS inside isolated containers to match the development environment, which is conveniently bundling dependencies and configurations. This basically helps us run ROS in all types of development environments. Yeah. Next, another thing we use for simulation is Gazebo. Gazebo is a simulation software where robot sensors publish data as it navigates an environment. Or basically, Gazebo is a realistic 3D simulator, and we can use it as a simulation for robotics, since it's very compatible with ROS. And Gazebo also has something called SLAM package, which makes it even more easy to use SLAM, as you can see by this image. So SLAM, what the SLAM package does is, as the robot navigates the environment shown here, the SLAM creates a 2D map of the environment showing position, buildings, rooms, etc. It creates a 2D environment. It estimates the robot's position as shown here. It shows a path the robot's taking around the room, and it shows a live map with the robot's position and sensor readings, making it very useful for future experiments with SLAM. Next, we use mirror. So SLAM is very good. However, there are challenges which come with it. One big challenge is mirrors. Think about mirrors, right? It's difficult to distinguish. So SLAM, it uses sensors to go around the room and check what's around it to estimate the robot's position, and it uses optimization and factor graphs to optimize its paths. However, with mirrors, the SLAM sensors often get confused because of the light reflected. This leads to errors in position, inaccuracies, and more errors in like SLAM. For example, with mirrors, a SLAM sensor might detect a phantom room when there is none, or might think you're going to a previously visited location when you are not. You're going to a new location because mirrors reflect data. So maps suffer from these interference, which is detrimental for SLAM. So one way to overcome this is use April tag for self-detection of the robot. To overcome this, we just have to teach a robot if it sees itself in a mirror, then basically it's going to a mirror because like if it sees itself, it's obviously at a mirror. So April tag is developed by the University of Michigan. April tags are a type of fiducial marker system designed for visual identification and pose estimation, which the robot can use to estimate its position by sensing itself in the mirror. We use tag family 36H11, which we placed an April tag on a robot and reflected it over its y-axis on the robot. And then that's just one tag. And then for double tag pose estimation, where we put one on the mirror, we also place an April tag on the mirror. First, start off with the easier one, which is double tag pose estimation. So if we're given the 3D position of a robot's virtual tag and the mirror's tag, we compute the mirror normal vector, which is what we get using this math formula, or we convert mirror rotation vector to rotation matrix by Rodriguez rotation formula shown here. And we also use tag's local coordinate frame. Tag's local coordinate has the z-axis orthogonal to mirror plane, and we use this vector math to find the basically distance, and then we use we can use this to find the true robot's tag position. This is easier because there's a April tag on the mirror and an April tag on the robot, so it can identify itself. Next, here's the Ross nodes we used for double tag estimation. So one, here's a reflected tag transitional vector, which is a transitional vector from camera to a virtual tag. We also use a mirror tag transitional vector, which is a transitional vector from camera to mirror tag. See the data shown over here with math. So from this, we can see also from the picture shown as we did the project. And there's a April tag on the mirror and one on the robot. The robot can use this to identify itself and estimate its position by looking at the two April tags. Since we know the precise location of the mirror tag on the mirror, we are able to use the mirror tag as a landmark for SLAM to navigate around, which is very useful, as now it eliminated the challenge. Now let's go on to a new thing, which is harder. Single tag pose estimation. It is harder because we only have one April tag, which is on the robot. So, on the robot. And now, on the single April tag on the robot. So now, given the 3D position of the robot's virtual tag, we can compute the mirror normal vector. You can see this because the mirror lies midway between true and virtual tag. So the plane normal is along the vector connecting them. You can see this through the math formula as shown here. Next, here's a mirror offset from camera origin. You can use a formula projection of midpoint to mirror normal. D is equal to negative NM. This is more math used to find the single tag pose estimation. And that's to find the shortest distance from true tag to mirror plane. We project the true tag onto mirror normal and we adjust it by mirror offset as shown here. Here's the Ross node we use April tag single tag, and these are all the data we got. You can see here, and this is a robot. There's only one April tag, and no matter angle it can found, and no matter what angle we did it at, we put the robot at, it can always identify itself at the correct position is that and treat this as a landmark. So as the mirror is relatively small, we can also treat the entire mirror as a landmark since now the robot identified itself and it identifies there's a mirror there. Now, in conclusion, we developed visualization for both offline and online SLAM for differential drive robots. Using able tags, we now treat mirrors not as an obstacle interfering with SLAM. However, we treat them as rather helpful landmarks used for like moving around a pathway and optimizing vector graphs. So limitations of our approach are that it may be difficult for the robot to see its own able tag when the mirror is like super slanted. That's like hard. We couldn't. That's like a limitation. Future work for this includes integrating these visualizations with real sensor data, like using an actual robot and integrating it with real sensor data, and expanding our mirror handling techniques to more complex reflective environments. We can also learn to quantify it, like quantify data, which is very useful to show results. All right, thank you. This is the project. I'd like to thank our mentor, Mr. Carlos Isaac Espinoza Ramirez, who was very useful for guiding us through this project. We'd also like to thank the SIP team for all their invaluable work and resources and giving us the opportunity to do this project. Unfortunately, my other fellow interns, Hansen and Jayoon, couldn't come here, so I recorded this. So, thank you.